In this video lecture, we will be solving this problem, shortest path with alternating colors. In this problem, we are given an integer n, which represents the number of nodes in a directed graph, and the nodes are labeled from 0 to n minus 1. That means we have a directed graph, and in the graph we have n nodes, with the numbering of the nodes starts from 0 and ends at n minus 1. There are two types of edges in this graph. Either it is a red directed edge or a blue directed edge, and there could be self edges as well as parallel edges. So in the input will be given two arrays, namely red edges and blue edges, where each element in these arrays represents a directed edge from node AI to node BI, where AI and BI are the nodes which are given for a particular edge. That means the edge is directed from A to B. What we have to do in this problem is that we have to return an answer array of length n, where each element, let's say element number x, represents the length of the shortest path from node 0 to that node x, such that the edge colors along the path alternates, or in other words, there are no two consecutive edges with the same color. So we cannot have any two consecutive blue edges or any two consecutive red edges. If there is no such path, then we return -1 for that particular node. Let's see the example test case. So in the first example, let's see the input and output format. So we'll be given the number of nodes n and two arrays representing the red edges and blue edges, where each edge is represented by a pair of integers representing nodes of the graph, which has a directed edge starting from the first element and directing towards the second element. And in the output we have to return n integers, or an array of n integers representing the shortest path till that particular node starting from the node number 0. Let's see the constraints of the problem. The number of nodes in the graph goes up to 100. That means the largest graph that we can have has 100 nodes, and the maximum number of edges that our graph can have are 400, while each edge is represented by a pair of integers, and the numbering of each node lies between 0 and n minus 1 if there are n nodes. Let's better understand the problem statement using an example. So here we have a example for the given problem statement. We have 3 nodes, and the numbering of the nodes starts from 0 and it goes till 2. So these are the edges that we have in the graph. The first edge is the red edge, which starts from 0 and is directed towards node number 1. So here it is represented in this way. The edge starts from 0, node 0, and is directed towards node 1. While this is the blue edge, which starts from 2 and is directed towards node number 1. Let's calculate the answer array for each of these nodes. Let's start from node number 0. What is the length of the shortest path which starts from 0 and ends at 0, and the edges must alternate in colors? That means we must have red edge, then we have blue edge, then we have red edge, and so on. Since we know that the target and the source node is same, the length is 0. We go to node number 1 here, and we want to know the length of shortest path which starts from node number 0 and ends at node number 1, such that the edges alternate in colors. And we see that there is only one edge which starts from node number 0 and is directed towards node number 1. Hence the shortest path has a length of 1. As we do not have enough edges, so that we check for the condition of no two consecutive uniform edges, uniform color edges. Then we move to the third node, which is node number 2, and in this node we see that we want to know the shortest path which starts from node number 0 and ends at node number 2, such that no two consecutive edges has same color. We can see that there is no such path, for we go from 0 to 1, then from 1 we do not have any directed edge which leads us to node number 2. Hence we return -1 for this particular node, and this is our final answer array. Let's see how we can solve this problem. So let's observe some of the facts about this graph. And the first fact is that this graph is unweighted. That means the weight of each edge is 1. That means to go from one node to another through a directed edge, we just add one step or a cost of 1. This is the first fact. Another fact is that it is a directed graph. So we want to find the shortest path to each node starting from a single node 0. So this is a single source from which we want to find the shortest path to all other nodes. And since we want a single source shortest path to each node in an unweighted directed graph, we can use BFS. That's the first observation. We can use BFS to solve this problem. So what do we do in BFS? In BFS we start from the source node, we push it into a queue, and then we explore all the adjacent nodes at the next level, that is this level, and so on. We keep on exploring each node till we reach our source node. And once we reach our source node, let's say S, then the path through which we have reached that node is the shortest path. And all we have to do is to validate that path, whether it is with alternating color edges or not. So that's the strategy to solve this problem. Let's see how we can build a working solution using BFS algorithm. So let's take this typical graph where the start node is node number 0 and we have total 7 nodes starting from node 0 till node 6, and we just have to modify our BFS algorithm a little bit so as to handle the condition of alternate color edges. For that we use a visited array of dimensions 2 cross n, where we have 2 rows and n columns, and but in the BFS we have to modify a little bit because we have to handle the condition in the shortest path that we have achieved for a particular node. We must not have any 2 consecutive edges with the same color. So how do we handle that condition? So we know in the BFS traversal, while visiting a particular node, while visiting a particular node, so as to ensure that the next node is visited with the color, so that the next node is visited with alternating color, we have to keep track of the color of the edge through which this node has been reached. That means suppose we have reached node number 5, then we must have information at this node of the edge through which this node has been reached. So we must know the color of the edge through which we have reached the node number 5, so that we can make sure that the next edge that we choose or the next node that we choose must have an alternate color edge. So how do we do that? It can be done by a little modification in the visited array. So this is the traditional visited array that we use in the BFS, but in this case, since we want to keep track of the color of the edge through which this node has been reached, we have to use another dimension which stores that color. This visited array is saying that whether this node has been visited or not using a particular color, where this color can be either blue or red, and we can represent blue and red with 0 and 1. 0 represents blue, 1 represents red. So this element is saying that whether this node has been visited using an edge of color red or not, and this element is saying whether the node has been visited with an edge of color. Okay, so this element is saying that whether the node has been visited with the color 0 or let's say red or not, and this element is saying whether the node has been visited using an edge of color blue or not. So if the node is let's say 5, then this node 5 can be visited using an edge of color blue, which starts from node number 2 and ends at node number 5. So the value for this element or this location will be true, while the node number 5 cannot be visited using an edge of color red. Therefore, the value for this particular location will be false. So this is how we use our visited array in this algorithm. So knowing this information for a particular node, we can take our next step in the BFS. So if it is visited using blue edge, then it then the next node can be visited using the red edge, and vice versa. If it is visited using red edge, then the next node can be visited using a blue edge. So that's why I'm using this visited array. So let's better understand the algorithm using an example. Okay, so let's understand the working of this algorithm, which is the modified BFS. So let's understand the working of this algorithm. In this algorithm, we start from the node number 0, which is the starting node, and we push a triplet corresponding to each node into our BFS, where the three integers in the triplet represents the node number, then the steps to reach that node, and the color of the previous edge. Fine. So this is our queue, and this represents the back of the queue. This is front of the queue. This is our answer array, and this is our visited array, which is used to mark the visited nodes of the graph. So initially we push 0 0 minus 1, the triplet corresponding to node number 0. So this represents the node number 0, and we have taken 0 steps to reach the node number 0, while there is no previous edge for this node. Therefore we push -1, and we mark these two positions as true because we are not visiting node number 0 again, as it is pointless to visit this node again. That's why we marking it as visited at the very start of the algorithm. Then we run our while loop. In the while loop, we first our only element that we have in the queue, that is the triplet 0 0 minus 1, and then we remove this triplet from the queue, and corresponding to node number 0 that we have extracted from the queue, we traverse the adjacent nodes, that is the node number 1 and node number 2, and we can see that we take one step to reach node number 1. We are using a red edge. Let's say 0 represents a red edge and 1 represents a blue edge. So the triplet corresponding to node number 1 would be 1 1 and 0, and we mark this node as visited in our visited array. So for node number 1, we mark here to be visited because we are using a red edge, and we push this triplet into our queue. So we are pushing this triplet into the queue, that is 1 1 0. Then we are also visiting node number 2, and the triplet corresponding to node number 2 would be 2, and the steps taken is 1, while the edge used is a blue edge. So we put 1 here, and for node number 2 we mark it as visited here, and we push this triplet into the queue, that is 2 1, while we also have to update our answer array. So initially, while we were at node number 0, we simply had 0 distance to reach this node, while to reach node number 1 we just took one edge, hence we put 1 here, and so for node number 2, the shortest path to reach node 2 is also of length 1 because we are using only one edge. Then we pop our front element from the queue, which is the triplet 1 1 0 corresponding to node number 1, and we remove it from the queue. Then we explore the adjacent nodes to the node number 1, which are node number 3 and node number 4, and the corresponding triplet for node number 3 would be 3, and the steps would be one step more than the parent node, which is 1 plus 1, and 2 would be 2, as we have taken 2 steps to reach node number 3, and the color must alternate. So if we had 0, then the color that we have here for node number 3 must be 1, and it is the case. We are using a blue edge to reach node number 3, so we are putting 1 here, and so we mark this node, that is node number 3, as visited in our visited array. So node number 3 is visited using a blue edge, so we put 1 here, and we push this triplet into the queue, and so we update the answer array for node number 3. So we have taken 2 steps to reach node number 3, which is the shortest path indeed. Then we pop our triplet, which is 2 1 1 corresponding to node number 2. Then we have to explore the node number 4 as well, because it is also adjacent to node number 1. Therefore the triplet corresponding to node number 4 would be 4, and we have taken 2 steps to reach this node, that is the steps taken to reach node number 1, which is 1 plus 1, and the color of the last edge is blue. So 4 to 1 is the triplet corresponding to node number 4. Let's update the data for node number 4 in our answer array. So we take 2 steps to reach this node, and this is the shortest path, and we mark it as visited in our visited array. So to reach node number 4, we are using a blue edge, and we push this triplet into the queue. Then we pop our triplet corresponding to node number 2 from this queue. So that is 2, 1 and 1. And then we explore the nodes which are adjacent to this node, that is 5 and 6. And the triplet for 5 would be 5. Then we take 2 steps, that is steps taken to reach node 2 plus 1, that is 1 plus 1, which is 2. And we reach this node using the last edge of color red. Hence we put 0. And it is an alternating color, therefore this is a valid. So we push it into the queue. And we update the data for this particular node in our answer array. So we have reached node number 5 using exactly 2 steps, and the last edge used is red. So we mark this node as visited in this visited array. Then we have node number 6. Then we have to visit node number 6 as well, because this is also adjacent to node number 2. And the triplet corresponding to node number 6 would be 6, and we have taken 2 steps to reach this node, while the last edge used is red. And hence we update the data for this node into answer and visited array. So in the answer we put 2 here, and in the visited array we are marking it as visited, while the last edge used is red. And we push this triplet into the queue as well. So we push it into the queue by 6, 2, 0. This is because the edges are alternating. The parent node is 2, and it has been reached using a blue edge, and the next edge is red. Therefore we can reach 6 from 2. So this path is valid. Now we have our answer array prepared, as we have exhausted or visited all the nodes of this graph. And this is our answer. That's how we obtain our answer using a modified BFS. So let's see the implementation for this algorithm. Okay, so this is the implementation for the modified BFS algorithm. This is the function shortest alternating paths, which takes in the number of nodes in the given graph, red edges, blue edges, red edges and blue edges. Then we initialize a graph in the form of an adjacency list which has a nodes n. Then we iterate over the red edge, we iterate over the red edges, and we push a pair for that particular edge, where the first element represents the node towards which this edge is directed, that is the edge is directed from the first integer to the second integer, while this integer, that is 0, represents the color of the particular edge that we are using. And since we are using a red edge, that's why we are pushing 0, as 0 represents a red edge while 1 represents a blue edge. Same goes for the blue. The first integer is the node from which the edge is directed, while the second integer is the node towards which the edge is directed, while the 1 represents the color of this particular edge. Then we declare an answer array of size n and initialize it with -1, and we declare a visited array of dimensions n cross 2, fine, which is used to mark the visited nodes of the given graph with the particular previous edge. And then we declare a queue to perform our BFS, and we push the corresponding triplet for the node number 0. So this represents the node number 0, this represents the steps to reach that node, and -1 is the color that we have used. Since we haven't used any edge, so we push -1 here, and we mark the visited cell for the first node to be true, because we are not visiting this node again. We are also storing 0 for the node number 0 as the answer, because that's the length of the shortest path to reach this node. Then we perform our BFS. While the queue is not empty, we pop the front element from the queue, and we iterate over all the neighboring nodes of the given node. Each neighboring node has a node number and the color of the edge. Then here we are checking if the particular adjacent node is visited or not using that color. If it is not visited and the current color or the color of the current edge directing from this node to this node to neighbor is not equal to the previous color, then that means this neighbor can be added as the next node to our shortest path, or this can be included into the queue. So we mark it as visited, while we push the triplet corresponding to this neighbor node into the queue, and the steps taken to reach this neighbor node will increase by 1. Fine. Then we check if the answer for this particular neighbor is -1, that means we haven't evaluated the answer for this node. Then we update the answer array for this neighbor node and with the number of steps that we have taken to reach this neighbor. So in this way we are performing the BFS, and finally we have our answer array prepared and we return this answer array right from here. Notice that whenever we reach a particular node through a valid shortest path, then that path will be the shortest path, because that's the property of BFS that we are exhausting, that we are using. Fine. So let's discuss the time and space complexity for this implementation. As we are using BFS, we know that the time complexity for BFS would be big of n plus e, where n represents the number of nodes and e represents the number of edges in the, while the space complexity is also n plus e because we are using a queue and a visited array. Let's move on to the implementation part. So this is a solution class where we have this shortest alternating paths function, which takes in the number of nodes in the graph, red edges and blue edges, and it returns me the answer array, which represents the shortest path to each node. So initially we declare a graph of size n, then we prepare our graph from the given red edges and blue edges. Then I declare my answer array, and this is my visited array used to mark the visited nodes of the graph using a particular edge. Then I declare my queue, which will be used to perform the BFS. Then I'm inserting the first tuple starting from node number 0 with steps 0 and undefined color -1, while I'm marking the visited cells for the node number 0 as true. And we initialize the answer array for node number 0 as 0 because the shortest path to node number 0 has a length of 0. Then I'm running my BFS. So in the BFS, I'm simply iterating until the queue is not empty, and I extract the front element of the queue, and then I segregate all the 3 elements of the given tuple representing the node, steps and previous color, and I pop that element from the queue. Then I traverse over the adjacent nodes of the given node, and I'm checking if the neighboring node is visited or not. If it is not visited and the previous color is not equal to the current color, then this node can be visited, and hence we mark it as true while pushing the new tuple for this particular node, and the number of steps to reach this node will increase by 1, and we update our answer array as well. So if the answer array for this neighbor is -1, then that means we haven't computed the result for this node yet, hence we reinitialize the array with the number of steps taken to reach this node. And finally, I'm returning my answer array right from. So this is the implementation in C++. Let's see the implementation in other languages. So this is the implementation in Java language, and this is the implementation in Python language. So that's all for this video. If you like the video, then do like it and make sure to subscribe to my YouTube channel, and do not forget to give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye.